right, continue our formal derivation of the work-energy theorem, then we'll get back to our energy accounting. We're going to go deeper into it too. So let's look and see what we can derive. What do we got? We're doing the mechanical work-energy theorem. Now notice I did before work-kinetic energy. Now I'm doing work-energy. This is theorem, I call it form 2. This is the one that you really use, okay? Now, remember that mechanical energy is defined as all types of kinetic energy, rotational and translational, we'll do rotations later, and all types of potential energy that are present or in play. Really, we're going to see that we define the change in potential energy, and we define that as the negative work done by a conservative force. Hold on, we'll clarify that, okay? You need to remember that we're going to start with form 1, so make sure you can do that derivation. The net work from all forces on our object will cause a change in kinetic energy, okay? So that's going to be interesting, and again, we're going to go back to work and define that more carefully. So how do we do this? How do we take kinematics and force analysis and turn it into an energy? We juggle. We just move things around, right? So we just move things. I just wanted to do that. Okay, so we move things around. You need to know the difference between conservative and non-conservative force. Let's begin that understanding, and we'll go back to a little more rigorous definition later as we go. So I've got 2 columns here. Conservative force, FC. You'll see this often. F. Make that nice and big. F sub C. Any conservative force. There's a whole bunch of forces that are called conservative forces. And then non-conservative, or FNC forces. Okay, and we'll talk about those. So there's an important distinction that allows us to define potential energy. And we'll see. And lots of really cool, deep stuff. So, intuitive conceptual understanding. Here's a really nice, I think, description. If a conservative force, any type of force that is in this class called conservative, slows down an object, decreases the speed of an object, it will or it can speed it back up. Okay, so if it takes away we'll get to that later. Non-conservative, if a non-conservative force slows an object down, it's not going to speed it back up. Just think of sliding something on the ground. Friction slows it down. Friction isn't going to speed it back up. I go like this, gravity slows it down and then speeds it back up. We'll talk about that in a moment. Okay, so here we go. I can think of that in terms of energy. So this is good to have the simple definition. That is, if the conservative force takes the kinetic energy away, it can give it back. If you let it, right? It will. It's as though the conservative force is storing the energy in some sort of bank for later use. Oh, it's stored. It's not, but there's no pockets, right? It's not really a bank, but that's how our energy accounting is going to be done. So the stored energy is a way of thinking or accounting for the energy. And this is the potential energy or change in potential energy. So that's the potential energy. But really, there's no stored energy, but we think of it that way. We account for it that way. I'll show you the quick sleight of hand where we do that, all right? Now, as far as non-conservative goes, that's either just going to take it away, or you can push something and give it energy too. But it isn't an automatic, I take it away, I give it back, right? Okay. So you don't need to overprocess it too much. You'll get it in time. Examples. So conservative forces for the mechanics course of physics, we deal with the gravitational force and an ideal spring or Hooke's law force. So that's all you really need to worry about. Occasionally you get thrown some other force that you're just given and you just take it and go with it. Later you'll get the universal gravitation force, which is gravity written as that GMM over R squared, if you recall. There's the electric or Coulomb force, and there's some really cool subtleties that you'll get to later. There's atomic forces, nuclear forces, things like that you can model with those U versus X graphs. So as far as you're concerned, we're really going to worry about those guys for now, and you'll get used to it. Non-conservative forces involve everything else. Friction, normal force, tension, your hand, whatever, okay? That's it. All right, so we're coming over here. Coming back over to this side, and we're going to explore these guys here, all right? So let's do the old toss-up, all right? So let's look at this. As you throw a ball up at some speed, it goes up, stops, and goes down. right? Stops for a moment, still accelerating. The velocity at the instant is 0, but the acceleration is not 0 because it's still changing. Only stops for an instant. As it goes up, gravity slows it down. The force of gravity takes the kinetic energy away, and it puts it in the united bank of gravity, or something like that. U, right? Potential energy, U. And there it is, in the bank somehow. But really what's there is the force of gravity. So potential energy is kind of a made-up thing, and we'll see that it makes our energy accounting easier. It's not there. In fact, it's an interaction. Forces are interactions, right? There's a force of gravity between the ball and the Earth, right? But, you know, again, we'll analyze it with that insight in mind. The force of gravity takes the kinetic energy away, stores it, not really, but our way of thinking. The force of gravity is ever present, so it will then increase the speed. It'll be back at the same speed. It'll give back the kinetic energy it took away. Okay? Fine. But on the way up, if it's an object that isn't too massive, or you know, if it's a feather, then we know that there is some drag. In fact, on anything, there's a little bit of drag. And the drag force as you're moving up is downward, so that's going to take energy away. But as you're moving down, the drag force is up. It's opposite the motion, just like your hand going through water or air, right? And that's going to take energy away too. So taking energy away, not ever giving it back. That's a non-conservative force. And you'll see, since it took energy away here, it won't go as high, right? Because gravity is at play while you're doing that as well. So that's one distinction between conservative and non-conservative force. Another example, oscillating back and forth on an ideal spring, right? A linear spring, a Hooke's law spring. Take this object. We're going to pull it out here and let it go. So it's going to move this way, and the speed will increase, and then the speed will slow down and decrease. But the speed is over here to the left. What direction is the force of the spring? Well, now when it's stretched, of course, the force of the spring is this way. And since the spring force is with the velocity, it's giving it energy, right? It's increasing the kinetic energy. But now as it comes in here and starts compressing, the spring force is this way. So now it'll slow it down or take away the energy. But as it expands, now the spring force gives it back. And so at that moment here, we say it's stored in the united bank of ideal springs, or spring, or elastic, right? But it's not really. It's there because there's a force there, a conservative force that is about to give it back, right? And it gives it back. Now as it moves out here, it's going to stretch back here, it's going to slow you down, and then it's going to speed you back up. Take out kinetic energy, give it back. So what's another example of non-conservative? Non-conservative would be friction. So as this slides in here, we got a friction force here, this way, opposite the motion, and this way. Opposite the velocity, taking away energy, taking away energy. Now it goes this way, and friction's this way, right? Friction is this way, taking away energy. Solid friction, just like a fluid-solid friction of the drag, right? So that's non-conservative, that's conservative. Okay, fine, now you have it, go with it. Let's do this derivation now. All right, let's do this derivation. It's all ticking away the time, that's good. All right, you can do this pretty quickly. It's magic, it's juggling. We're going to juggle these factors around. I'm going to do it a particular way here. Okay, you ready? We're going to take what we knew, the work from all forces on some receiver causes the change in kinetic energy of that object. Okay? We defined work before. All right, so that's good. Cool. Now, what is this? Well, this is kinetic energy later minus kinetic energy earlier. And what is this? Well, I'm going to break that up now. I'm going to break that up into work from non-conservative forces plus the work from conservative forces. Because it's going to allow me to do a little shifting of my theory that makes for nice energy accounting. Okay, cool. And now I'm going to do a little game here too. I'm going to go, let me just play with this. I'm a theoretician again. I'm going to go, that's work Non-conservative equals kinetic later minus kinetic earlier. And I'm going to take that guy and put it right over here and say minus work from all conservative forces. All of them that are present. All right, cool. And now I'm going to mess with it. And this wasn't done in, 5 minutes, right? People had to think about this. Hey, I got another way to do this. Let me make this little shift here. I'm going to go, all right, I got the kinetic energy later minus kinetic energy earlier. I'm going to take this guy and I'm going to say plus. And I'm going to take this whole guy here and just put it in parentheses. Minus work conservative. Because there's something special about it. I mean, that force, when it takes energy away, it gives it back. Okay, cool. So, doing that. Now, notice that work, this is an important point, is done between two states. We say it's not a state function. At any moment, I can have kinetic energy. At any moment, kinetic energy. But work is done between the states, right? So this is all earlier to later. That's our interaction form, as you recall. So this is earlier state to later state. And this, too, is earlier to later. And it's a little bit of a drag because you have to watch how it moves from earlier to later. Except we can do away with that, at least here. We can't do away with it over here. And so how we're going to do that is go, hey, wait a minute. This is the kinetic later minus kinetic earlier plus, and here's the magic, instead of having to follow it from earlier to later, I can turn this into something. I can invent a new idea of stored energy. I pretend there's a bank. And that negative work from conservative force is the negative potential energy, the negative work from the conservative force is the change of potential energy. And this is for all, or every conservative force will have its own potential energy. So for all, or each, if you will, it's fine like that. Okay, cool. So let me rearrange that. Just juggling, right? All I'm doing is crazy. KL minus KE plus, well, what's the change of potential energy? Well, UL minus UE. Hey, I got an idea. Let's do this. Let's do this, and let's do it in red because it's kind of cool. I'm going to just look KL plus UL minus KE plus UE. And what did I gain? Well, I gained the fact that I don't have to go from earlier to later and follow the path and see what's happening. You don't have to at all. If I've got a function here that I can use as a state function, rather than a path function, it's much easier. And so that's why we invent this thing. And what do we call that? Well, this is called the mechanical energy later minus the mechanical energy earlier, right? Or if you want, delta E. And what's it equal to? It's the non-conservative work from earlier to later. And what's true? If that's zero, we have conservation of mechanical energy. So I would look at it this way or that way, either way, as form 2, and that's the energy accounting that we had been doing and getting used to. And look how beautifully it came out. Remember that derivation? Then splitting it and realizing the character of a conservative force is different than the character of a non-conservative. Since a conservative force will give back the energy, it's really only holding it for you, right? If you take some of your money and you put it from a checking account to your saving account, you still have the same amount. It's just changing forms, right? Here we go from kinetic to potential back to kinetic. If you take some energy, if you take some money and you give it to the person at the store, well, then you've lost that money, haven't you? Keep in mind though, this is a clever device for accounting. Behind the scenes, in reality, there is a force at play and there's no bank. And the definition is here. The definition is that the change in potential energy from earlier to later is for some conservative force, and that is, by definition, the negative of work from that conservative force. And that's the invention. But rather than having to follow the force over the path, we can just look at earlier and later, independent of how it got there. And we are cool, and you are rock and rolling. And now we've got to get into a little bit more mathematics, derive some particulars for which forces? Gravity, just mg, mg down, and the ideal spring, that negative kx. Force will derive, well, you know what those are. You know what U is. It's mgh, and you know what U for an ideal spring is 1/2 kx squared. How do you get that? I'll show you next time. And we also need to then explore a little bit more of the definition of work. And we'll look at the integral form of the definition and the derivative form. Really hold on tight to that, because that's going to be your stepping stone into more advanced, more technical kind of work. And it doesn't have to be that mind-blowing once you get a solid footing on that. So I think we're good to go. Play with it. Go back to your old energy accounting. Now you have formally been introduced, and you can do it too, right? So do it as many times, twice a day, 3 times a day. Whenever you eat, sit down before you eat, do your derivation. Form 1, followed by Form 2. Bada bing, you got it. Okay, ciao.